before we get started today? We all good? And maybe just note about the extra credit. I will award the credits for on the exam. I'll do that after Friday. So that hasn't shown up yet if you've been wondering about that, but it will. Okay. Well, we're going to finish up our discussion on chapter 8 today. But before we start with some new material, I wanted to go back and reiterate something from an example we did on Friday, which I wanted to just make sure we're a little bit more set on, due to the fact that there's some issues with that on the homework assignment. So, just to remind you, kind of where we're at here with our discussion on the hypothesis testing. Sort of the four situations that we considered. These are the same four that we looked at with confidence intervals in chapter 8. We have the first three are talking about a test for a population mean. So we have we're saying something about population mean mu, and we have a normal distribution with known variance, we have a normal distribution with unknown variance, or sort of the most general case, which is what we'll talk about today. We don't know what the distribution of our random sample is, and therefore we also don't know what the variance is. And then we'll also talk today about doing a test for a Bernoulli random variable, which is something we looked at in chapter 7 for confidence intervals as well. Okay, so going back to this example from a little bit earlier in the chapter, this is on this was the melting point example. We did a hypothesis test, but then the second part of this question asked for, we wanted to find the probability of a type 2 error. This relates to something that's in your homework problem. So again, if we have a level 0.01, if our significance level is 0.01, we want to know the probability of a type 2 error when the mean mu is actually equal to 94. So if you remember, our alternative hypothesis, sort of the initial thing we talked about here was we wanted to see if our population mean, the true average melting point, was less than 95 degrees. And so again, kind of thinking about our decision rule for these tests, again, we're going to reject the null hypothesis if our p-value is less than 0.01, and we're going to fail to reject if the p-value is bigger than 0.01. And then what we worked through in the calculation we did was to figure out sort of what value of our sample mean x bar would give us a p-value of less than or greater than 0.01. So that's the 94.301. So if our sample mean was less than 94.3, we were going to reject the null hypothesis, and if it was bigger than, vice versa there. Okay. So then here we want to figure out the probability of a type 2 error. So again, we worked through all this already on Friday. I just wanted to hit it again. Remember the probability, a type 2 error is one of those two errors that we can make. We have a type 1 error, which is rejecting the null hypothesis when we should not have rejected it. And here a type 2 error is saying that we failed to reject the null hypothesis, which is what we indeed did here. When in fact the null hypothesis was false. So we sort of said that at the end of the day the null hypothesis is what we're going to go with, but in fact that is not true. So we can calculate the probability of this error given certain values of the population mean mu. So if the population mean really was 94, I can find the probability that I failed to reject the null hypothesis. So again, remember the null hypothesis said that mu was equal to 95. So if the mean really is equal to 94, then the alternative hypothesis is true. So if mu really equals 94, then the alternative hypothesis is what we should have decided on. Okay. So going back to what I had on that previous page, I failed to reject the null hypothesis when I'm down here in this case. So when the sample mean x bar is bigger than 94.301. So that's when I failed to reject the null hypothesis, and I can find the probability of that for a particular value of mu. So then what we talked about was if the mean really was 94, then the distribution of x bar is normal with mean 94, and then variance is the same as it was before, sigma squared over n. And that's how we get down to this bottom row. So again, the probability that the sample mean is bigger than 94.301, when the true mean is actually 94, I can do this calculation here. So this is the way that you would, if you're asked to find a probability of a type 2 error in your homework, this is the way that you would go about doing this. Questions or comments you guys can think of here? Yes, sir.
Yeah, on the homework, if it doesn't tell us it's a normal distribution, but n is greater than 30, can we just say by the central limit theorem, can we apply that to the hypothesis test?
Yes, exactly. That's what we're going to talk about next. So, yes, definitely. So, exactly the right intuition there. Okay, so again, I'd encourage you to follow this sort of framework when you're finding the probability of a type 2 error. The homework does also ask you to find, in one case, I think in the very first problem I was talking to Mary, it asks you to find the power of the test. So if you look back in your notes, you'll remember that the probability of a type 2 error is 1 minus the power. So similar, the power would be just 1 minus the probability of a type 2 error. So what the power is saying, that's telling me the probability that I rejected the null hypothesis when the null hypothesis is false. So that's kind of, you want that probability to be high, right? The type 2 error is I've made the wrong decision when the null hypothesis is false. The power is what's the probability that I make the correct decision when the null hypothesis is false. So you can calculate either one of those things and just take a little 1 minus to get to the right number there. Okay. Moving on to some new material then. This is not sure exactly what page this is. This is 3. This is page 11, I think, of your chapter 8 notes. We're going to talk about this third situation, which is what the question that Jamie just asked. So what if I don't know what the distribution of my random sample is, and I don't know what the variance of my population is? So what do we do in this case? Well, it's going to be very similar to what we've done in the previous two cases here. So we've already talked about these first two, and it turns out that we'll do exactly what you think we're going to do, and kind of draw back upon the ideas of the central limit theorem that we talked about in chapter 7 as well. So when we're in this case, you're going to follow the same steps that we've been following all along. So I'm not going to write these out because we've already sort of talked about what these are. I'm going to define our parameter of interest. So we're talking about the mean mu still. Set up our hypotheses. That's going to be based on the question that we're looking at. And then we're going to observe a random sample. So that's x1 up to xn, their IID, some distribution. We'll call that a capital F. And we don't know what this is. We don't know what the distribution is. And we also don't know what the variance sigma squared is. Okay, so that's just kind of the setup. But regardless, our test statistic, so sort of in our next step here, performing the test procedures, the test statistic is very similar to what we've seen before. We still have x bar minus the hypothesized mean, and we're dividing by something that looks like the standard deviation, but instead of sigma in there, we have our sample standard deviation s. So then what the question Jamie just asked again, if the underlying distribution is not normal but our sample size is large enough, then this statistic will approximately have the t distribution that we looked at in the previous case when I had a normal distribution and unknown variance. So even if my underlying distribution is not normal, or if I don't know what it is, as long as my sample size is big enough, then I'm okay here. And so again, we just need to check this condition again, that's making sure that our sample size is indeed large enough. Okay, and large enough here we mean that n is bigger than 30. It's a little bit arbitrary. But that's kind of our rule of thumb that we'll use here. Okay, and then of course we'll make our conclusion again. We'll reject or we'll fail to reject. Then make sure to give a good interpretation of what that means in the context of the problem. So again, nothing really new here. It's just now we're sort of moving from that second case to this third case. We're saying we don't know what the distribution is, and we can still do sort of the exact same procedure as long as our sample size is big enough. So yeah, questions or comments you guys can think of before we jump into an example? It's kind of exactly what you would have expected to happen here. Okay. Well, let's try applying this procedure here. Okay, so here we're going to look at eyeglasses. We have a random sample of 50 lenses used for a particular type of eyeglass, and we find that those 50 lenses have a sample mean of 3.05 millimeters and a sample standard deviation of 0.34. So maybe if you're a manufacturer here and you know that the average thickness of these lenses should be 3.2. Do the data that I've collected here suggests that the true average thickness of these lenses is something other than what I want it to be. So I want the average thickness to be 3.2. Do this data tell me that I have something else going on here? Okay. So let's try to set up a hypothesis test based on this question here. So what we want to say something about is the parameter mu, which is the true mean thickness of these lenses. Okay, and then let's set up our hypotheses. So I have my null hypothesis and my alternative hypothesis. Both of them are involving this parameter mu. And I always have an equal sign in my null hypothesis is what we're going with here. All right, so who can help me out? What number do I want to put in there after the equal sign for my null hypothesis? So remember the null hypothesis is always kind of sort of assuming that nothing is going on, and the alternative contains our question of interest. So the alternative, maybe actually let's do that first and figure out what our alternative is based on this question that we want. So again, we're saying, do the data strongly suggest that the true average thickness of these lenses is something other than what is desired? So what can I fill in here? What does that mean about my parameter mu here?
Just say it's not equal to 3.2.
Exactly right, yeah. So my parameter here, I'm saying I want to know if that true average thickness is not equal to something other than what I want it to be. So I don't care if it's bigger or smaller. I just want to know if it's something other than. And then I can plug 3.2 in here as well. Okay, everybody all right with that? Okay, so now again, before we jump into our calculations, we want to make sure that we're okay to use this procedure here. So, so can we use a t-test? So this involves our conditions. So what two things do I need to be true here? Well, I guess so. First of all, let's just note that I don't know anything about the distribution of these, the thickness of these eyeglasses. Right? It doesn't say the distribution of eyeglass the eyeglass thickness is normal, or it doesn't say anything like that. Right? So we're sort of in this new case that we're talking about here, this unknown distribution. I need to make sure that I have a random sample. That's sort of always there. And is my sample large enough? Okay, so do I have a random sample here? Everybody said yes. It is stated in the problem. And of course my sample size here is 50, which is bigger than our 30 cutoff, so we're good to go there. So can I use a t-test? Well, of course I can, right? But again, just want to make sure when you don't know the distribution, you want to make sure your sample size is big enough to make sure you're not going to get some funky result going on here. Okay, so then we want to calculate our test statistics. So we want to calculate our test statistic t, which again is x bar minus mu 0, our hypothesized value, divided by the sample standard deviation over the square root of the sample size. So our sample mean, we're told in the problem, is 3.05. What is mu 0 here? I think I heard it. 3.2, right? That's the value that's coming out of my null hypothesis. My sample standard deviation S is... What's my sample standard deviation? 0.34, yes. And finally, my sample size, of course, is 50. So maybe just to point this out, so usually in these problems, in your homework problems, I'll tell you sample mean x bar, and I'll tell you a standard deviation, right? So it's not always... I think that it can be tricky to figure out, am I given the population standard deviation or the sample standard deviation? And you just want to make sure that you're kind of read the question carefully. So is the standard deviation I'm giving you talking about the sample that we've collected, or is it something about the population overall? Here it's maybe quite obvious. I say sample standard deviation there. But just think about, what does the standard deviation correspond? Does it correspond to my sample, or does it correspond to the population in some sense? Okay, anyway, so we have everything we need here to calculate this test statistic. So this is 3.05 minus 3.2 over, and if you work that out, you should get negative 3.12. Okay, so here our test statistic t is negative 3.12. Now to find our p-value, so we're going to use the p-value to make our decision here, right? So our p-value, again, we want the probability that our let's sketch a little picture here. This is my t distribution centered at 0. And my test statistic I got is down here, negative 3.12. What shaded in area in here is going to represent my p-value? The upper part that's 3.12?
Like that's past 3.12.
Positive 3.12?
Yeah, would it be the positive and negative since it's not equal to?
All right, so it's both the positive and the negative, right? So remember, my alternative hypothesis was that the mean is not equal to 3.2. So my p-value is going to include both tail probabilities here. So this is up here is 3.12. So these things together will give you my p-value. Okay, so that's probably that a t random variable is bigger than, we can do 3.12, and then actually we want 2 times this probability. Okay, so how do we find that? Well, we can go to our table, but to use the table we need to know what our degrees of freedom are. So here I've actually included this table in here. This is the one that's in your notes on that previous page there. Again, this is kind of like the standard normal table, right? So what we need to figure out, we need to list what our degrees of freedom are here. So what are my degrees of freedom here?
49.
Say again?
49.
49, right. So it's n minus 1, which is 49 here. So I want to find the 49 column of my degrees of freedom here. I don't see 49, so what do I do? Yeah, round down, right? So you can use degrees of freedom is 40. So here's my degrees of freedom column. And then over here, I find my test statistic, which was, again, pretty close to 3.1, or negative 3.1 anyway. So I can trace this over and find that the probability of being larger than 3.1 is 0.02. Okay, so again, this is my p-value is approximately equal to 2 times 0.002, which is 0.004. Yes, sir.
If our t-value had been like 3.16 or 3.18 or something, do we still use the 3.1 column?
Good question. So if your test statistic had been 3.18 or something like that,
Yeah, like close to 3.2, but it's not there yet.
but it's not quite to 3.2. Yeah. So there is a little bit of approximating going on here since we're using a table. It's not giving us. We don't have the exact degrees of freedom. We can't maybe look at the exact value of our test statistic. I guess what I would tell you is that if you look at the sort of the values around what we found, they're very, very close to each other, right? You're off by 0.001 maybe. So that's not going to be a big deal, I guess. So whichever way you round there is okay.
Okay.
Yeah. If you're using the table here.
Okay.
Yeah. It's a great question. Other questions about what we're doing here? How we found the p-value? No, that's okay. I think there is, or is there a way to use your calculator to find this p-value? Has anybody tried that? Is there a t-test? Okay, so if you have an 83 plus or 84 plus, something like that, Google search might be your friend there for being able to do this. That's totally fine if you want to do it that way. Okay, so regardless, we have our p-value here. So what are we going to do next? So we want to use our p-value to make a conclusion. So what is our conclusion going to be here? We're going to reject the null hypothesis. Why do you say that?
It's really valid with small p-value, so we have to have a really small significance level except the null hypothesis.
Yeah, excellent. Right. So the p-value is really small here, so we would need our significance level to be extremely small to sort of fail to reject here. But the good point is that I didn't actually tell you what a significance level here to use was, right? So we always want to compare the p-value to alpha. And what is alpha here? Well, I didn't tell you. So just a reminder that if I don't specifically say what alpha is, we can go ahead and use 0.05 is sort of the standard one to use. But it's a good point anyway that sort of whatever significance level we chose here, we would reject the null hypothesis. So there's sort of no chance that we would have failed to reject in this case. But let's go ahead and make our interpretation. So because the p-value is smaller than alpha specifically, in that case we're going to reject the null hypothesis. And so what does that mean here? Well, what that means is that that there is evidence to conclude that the true average thickness of these lenses is something other than 3.2, or is not equal to 3.2. Okay, so because we have a small p-value here, we reject the null hypothesis. And again, what that means, again, I always want to say what that means in a particular problem. So our interpretation is that means there is evidence to conclude that the true average thickness, so that this parameter mu that we're talking about, is not equal to 3.2. So maybe we need to fix our manufacturing process or something, but that is the conclusion that we can make. Everybody okay with the conclusion? Any questions you can think of? Is that okay? So again, always, when you find your p-value, make a conclusion, reject or fail to reject, and then always make sure to interpret. So either there is evidence to conclude or there is not sufficient evidence to conclude. It's kind of how you want to start those interpretations. Okay, so one more hypothesis test to discuss here, and this is this last situation where we're talking about a population proportion here. Okay, so and this is kind of building off of the ideas that we used in chapter 7. So if we have a random variable x, which is our binomial random variable, or the number of successes out of n trials, then what we've seen before in this class is that our sample proportion p hat has approximately a normal distribution as long as my sample is big enough. So this is sort of my large enough check here. So as long as those two things are true, then x has the random variable x has that normal approximation, which means that the sample proportion also has that normal approximation. Okay, and therefore we can standardize to get something that's a standard normal random variable here. Okay, so we're going to do the same thing that we've been doing before, but now we're talking about the proportion p. So here we're looking at p, which is the population proportion of, well, it's the population, I guess we'll say success proportion. So whatever it is that we're looking at in our example, we're looking at sort of the proportion of times that we have a success, whatever that is. So then our hypotheses, slightly different, but very similar to what we've done before. We still need a null hypothesis, H0, and that will always be that our population proportion is equal to some hypothesized value. So this is my hypothesized proportion. My alternative hypothesis will be one of three things again. And again, exactly what you expect. It's either it's less than my hypothesized value, it's greater than my hypothesized value, or it's not equal to this hypothesized value. Okay, and so then I'm going to observe my random sample now is abusing notation a little bit here, but my random sample is from a Bernoulli distribution with parameter p, which means that x either equals 1 or 0 with probability p and with probability 1 minus p. So each xi, I should say, equals either 1 or 0. So changing notation just a little bit here. Yeah, so I'm going to observe a bunch of things, a random sample of objects, and for each one I'm going to determine yes, it was a success, or no, it was not a success.
What does WP say?
Yeah, that is with probability. That's just harkening back to chapter, I think, 3, long time ago. Good question. Okay, so again, next step we're going to again actually do the test procedures, as long as maybe our conditions are okay. And here again, our test statistic is kind of probably exactly what you would expect it to be, with maybe one small change here. So what I'm dividing, so I'm taking my estimate minus the hypothesized value. So here's my estimate. I'm subtracting off the hypothesized value. But now I'm dividing by the square root of p0 times 1 minus p0 over n. So why am I dividing by p0, or something involving p0 there?
Because you're testing based on the null being true.
Absolutely right. So I'm testing I'm calculating this test statistic based on the idea that the null hypothesis is true. And so, why does that mean I have p0 in there?
Because you're calculating the probability with p0, and so if it is small, and based on p0 being true, that would be very unlikely.
Right. So based on so what the null hypothesis says is that the proportion p is actually equal to p0. So again, going back to this idea, because I'm saying the true mean is actually p0, I can plug that in here, and so that will I do my calculations based on what the null hypothesis tells me. The null hypothesis tells me that p is equal to whatever that hypothesized value is. So it's exactly what you just said. Thanks. Thanks, Kyle. Okay, so is everybody okay with that? Why we're dividing by p0 here? So you definitely don't want to divide by p hat. P hat times 1 minus p hat over n. That's what we looked at when we were doing confidence intervals. Here we put in p0 because that's what the null hypothesis tells us the value of p is. Okay, so then the check we need to do before we actually perform this test is, again, just make sure we have a random sample and make sure that these two conditions are satisfied. Again, it's involving p0 and not p hat like it was before, because that's what the null hypothesis is telling us again. So when you're doing your large enough check here, you want to make sure to use p0 and not p hat. Okay, so let's make a note of that. Use p0, not p hat, to check large enough. Okay. So then finally our conclusion here, again nothing new there. So here I've written that out a little bit more clearly, I guess. So when you're doing a hypothesis test for proportions, kind of like we did with confidence intervals, do I have a random sample, and then my large enough again involves p0. Okay, so after I've done that, I'll make my conclusion, I'll find my p-value, I'll reject or fail to reject and interpret. Again, all this is going to be sort of exactly the same as it was for the z-test, which was case 1 in this chapter. Okay, let's do an example here, or I guess any questions or comments before we jump in here. Everyone with me? Okay. All right. So here for my example, we're talking about the incidence of a certain type of a chromosome defect. So for the entire U.S. adult male population, it is believed, medicine tells us maybe that that true proportion is 1 in 75. Okay. So then I take a random sample of 800 people from who are prisoners from penal institutions, and I find that 16 of those 800 that I sample have this chromosome defect. Okay. So the question, there's my data. Told you I have information on 800 people, each of which, yes, they have this defect, or no, they don't have this defect. So can it be concluded from this information that the incidence rate of this defect among prisoners is different from sort of the assumed rate for the entire population? And I want to do this test. We'll use a significance level of 0.05. Okay. So what I want to use this data that I have to say is the defect sort of is the rate of that defect different in prisoners, in the population of prisoners, than it is in the sort of population of all adult males. Okay. Okay. So let's first, we want to again figure out what we want to test here and write down our hypotheses. So here, let's set up the notation: P is equal to the true proportion of prisoners who have the defect. And then I want to test some hypotheses here. So both of them are involving this parameter P. You can remember the alternative hypothesis always sort of contains our question of interest, so let's figure out what that is. We can then fill in the null hypothesis. So what's my alternative going to be? I want to see if this rate is differs from the presumed rate for the entire adult male population.
Not equal to whatever 75.
Absolutely. So my question, I want to see if it's different than 1 over 75, which is the rate for all adult males. So that's 0.0133. And so I'll assume the opposite. I'll assume that it is the same. So I'll assume that proportion is equal to 0.133 and see what the data tells me otherwise. Okay. Again, setting up hypotheses can be tricky. Is that okay with everybody?
So,
Yes.
H naught will always be equal.
Yeah. So the null hypothesis will always have an equal sign in it. Yep.
Is it important to include the other bits like greater than or equal to? Not really.
Yeah. So that's something we talked about earlier. So suppose I'd ask a question of, maybe what I'm really interested in here is the defect in this in these prisoners, is it greater than in the rest of the population, that or less than? I might really be interested in one of those things, in which case my alternative would be its proportion is actually greater than 0.0133. But if that was the case, we're still going to say use an equal sign in the null hypothesis. You can sort of keep in mind that what I'm really talking about is a less than or equal to, because if I want to see if this proportion is actually greater than something, if it's less than that, it might as well be equal to, right? So there's some details there that we're sort of glossing over, but even if your null hypothesis said less than or equal to, you would still do the procedure in exactly the same way. But sort of for the purpose of this class, you can keep an equal sign in there and kind of think about that. I am actually covering all values there. It's just I haven't really said that. It's a good question. Okay. Okay. So before I jump into my calculations here, I want to make sure that my conditions are okay, that I can use this procedure. So random sample. Do I have a random sample? Everybody said. Nobody said. Yes, okay. And why do I have a random sample? It's stated in the problem. Okay, and then my large enough, I want to make sure that n times p0 is bigger than 10, and n times 1 minus p0 is bigger than 10. Okay, so what's my sample size? Well, n times p0, what's my sample size here? 800. And p0 again is 1 over 75, which is 10.6. So we're pretty close. Sorry, let me rewrite this. 10.64. It's pretty close to 10, but it is indeed equal to 10, so we're good to go there. And n times 1 minus p0, 800 times 74 of 75. We're well in the clear here, 789.36. Okay, so our sample is indeed large enough. We're not going to have any problems when we do this calculation. Okay, so then my test statistic again is a z, which is p hat minus p0 over a square root of p0 times 1 minus p0 over n. Again, what's my sample proportion here? 16 over 800 minus 0.0133. And then I plug in p0 in the bottom, so 0.0133 times 1 minus 0.0133 over my sample size, which is 800. Okay, so if you work that out, I think that gives you something that's about 1.35. Okay. Okay, so I have my test statistic. I'm ready to calculate my p-value. So z equals 1.35. So my p-value, what is my p-value going to be for this alternative hypothesis? Yeah.
2 times z is greater than 1.35.
Excellent. Yeah, so it's just, I want to look at both tails here. I want to look at the upper and lower tail. So I take 2 times the probability that that a standard normal is bigger than 1.35. And again, you'll go to the table. You've done this a million times now. We're not going to look at it again. And you'll find that this is 2 times 0.0885, which is 0.177. Okay, so p-value is 0.177. What do I do? Compare it to my significance level, absolutely. So alpha equals 0.05. So p-value is bigger than alpha. So what is our decision? Am I going to reject or am I going to fail to reject? I think I heard it over here. Yes, we're going to fail to reject because our p-value is bigger than alpha. So because the p-value is bigger than 0.05, we fail to reject. Null hypothesis. Okay, so what does that mean? Well, what that means is that there is not enough evidence to conclude that the rate of this defect, that the let's say the defect incidence rate is different for male prisoners. Okay, so we failed to reject the null hypothesis. What that means is that, again, the way you start this off is that means we do not have enough evidence to conclude what our original question was. So, original question was, is the incidence rate different for male prisoners? And here we can't say that. We can't say there's not enough evidence to conclude based on the information we collected anyway. We cannot do that. Is that okay with everybody? Is this starting to feel a little more comfortable? It's very quiet today. Okay, well let's do one more example here to finish out the chapter. Shoot, I was hoping to have time. I was going to do an example from one of the extra credit data sets you guys submitted. We'll do that on Friday instead. Okay. So final example here. We have an article here that's reporting that in a random sample of female workers, 421 of them have body mass index of less than 30, and 120 of them have body mass index of at least 30, so 30 or more. So the question we're going to look at here, is there compelling evidence for concluding that more than 20% of female workers are obese or have a body mass index of 30 or higher? Okay, and so we want to state and test the appropriate hypotheses using alpha equals 0.05. Okay, so P here, what's the parameter I want to make a statement about here? Yeah, so this is the proportion of female workers with a BMI bigger than or equal to 30. Okay, so my hypotheses that I want to test. Again, they're going to involve this parameter P. So what's my alternative? So I want to know, is there compelling evidence that more than 20% of female workers are obese? So what's my alternative going to be? Greater than 0.2. So I want to see if this this proportion is bigger than 0.2. And again, in the null, I will just put an equal sign. So here's another good example. If that proportion is actually less than 0.02, it's sort of refuting my claim here anyway. So we'll just leave an equal sign in there, but you can imagine that it's including the smaller values as well. Okay, so we do have a random sample stated in the problem. And let's make sure my sample is large enough here. So n times, well, let's figure out quick what n is. So total I have 421 plus 120, or 541 people in here. And P0 is 0.2. So n times P0, make sure that's bigger than 10. And n times 1 minus P0. And I'll let you double check that's fine here. We're in good shape. Okay, so because we have a random sample, because our sample is large enough, we're able to proceed here. So let's figure out what our test statistic is. So the test statistic, again, is a z. We're going to take p hat minus p0 times 1 minus p0 over n. Let's just make a note over here. P hat. What is my p hat? So I have 541 total people. What goes in the numerator there? 120, right? I want to know the sample proportion of people in my sample who have body mass index over 30. So that's my p hat is 0.222. P0 again is 0.2 and n is 541. So if we plug all that stuff in there, you will get 1.28. Okay, so moving a little quicker now. So then my p-value, what is my p-value? How am I going to find what my p-value is here? Say it again, a little louder. I think you were right. Yeah, so you said the probability that a standard normal is bigger than 1.28. And why'd you say bigger than? Yeah, so that's what was in our alternative hypothesis. Remember, the alternative was that p is greater than 0.2, so we put a greater than in our figuring out what our p-value is there. Okay, and you'll again go back to the table and you can find that this is 0.1003. Okay, so p-value is 0.1. Alpha, we want to use a 0.05 here, so what's my decision? P-value is bigger than alpha, so what am I going to do? How about someone in the back there? So again, my p-value, this is bigger than 0.05. It's bigger than my alpha level, so someone from the back, am I going to reject or am I going to fail to reject? Fail to reject, absolutely. Yes, so I've run out of space, haven't I? So change colors here. So because the p-value is bigger than 0.05, I will fail to reject. And so then what does that mean in this case? Does anyone want to try to interpret that for me? So I failed to reject in this example. What does that mean?
There's not enough evidence to say that there's a higher proportion in point two.
Yes, exactly right. Very nicely done, Matt. So again, what that means is that my original claim was that, or my question was, are there more than 20% of female workers that are obese? And the answer to that question is no. So what Matt said was there is not evidence to say that more than 20% of female workers are obese. Nicely done. Okay, well, didn't quite finish up Chapter 8. That's okay. We'll wrap that up on Friday. Thank you guys so much for being here. Have an excellent day, and we'll see you on Friday. Oh, and I do have exams and homeworks if you're still looking for one of those.